Okay? All right.
Thank you.
So Joey had made this sundial out of cardboard. You could tell because it was cut out really badly. You could see the line that he had drawn. And I brought him over. I ranked him first because it was obviously the only one in the science fair that was actually built by the kid standing beside it. And I brought Joey over to the rest of the judges. I said, Joey, I'm going to ask you a few questions. He said, sure. He was very self-assured. I said, okay, can you use this sundial every day, all day? And he said, yeah. I said, really? Day and night, Joey? You can use this at night? And he looked and he said, no, no, no. You can't use it at night. You have to use it during the daylight. I said, that's good. And can you use it every day, a cloudy day? And he said, yeah, no problem. And I said, really? What if it's cloudy and it's raining? Can you use this? And he looked at me and he said, it's made out of cardboard. It'll get ruined in the rain. So he came 10th out of 10, but I've always remembered Joey as a prospective graduate student, actually, because it was so out-of-the-box thinking, right? So yesterday, down the hill, this is my first time up the hill. I used to live on the hill here on sabbatical. We'd look up here and wonder what was going on. I focused primarily on ice age sea level. I'm reversing today, and I'm including a bit more material on ice sheet stability and how sea level interacts with ice sheets, because I think this audience will prefer that. So we'll begin with part one, the sea level fingerprints of rapid melting. Rapid here means any melting that has a time scale up to 300-400 years, right? Because on that time scale, the Earth's response to an adjusting ice sheet will be primarily elastic. One doesn't have to include viscoelastic effects. In ice age work you do, it's a slightly more complex calculation. All sea level calculations are relatively complex, and there's a simple reason for that. Sea level, or water, meltwater, goes where gravity tells it to go. However, if you move water around, or if you melt an ice sheet, you are moving mass around. The adjustment itself perturbs the gravity field. So by moving water around, deforming the Earth, you are influencing the gravity field, and in turn you're governed by the gravity field. That leads, for those mathematically inclined, to an integral equation that's colloquially called the sea level equation. And that equation has sort of existed in the literature for about 35 years, and it's been revised to include more and more complexity. For example, including marine-based, grounded marine-based ice sheets in sea level codes was only done correctly in the last 3 or 4 years. So it's a process that continues. So I won't talk about the technical detail, but I do want you to understand that that exists behind here, and I'd be happy to take as many questions as necessary. I'll focus here on the 20th century, just to give you an idea for one of the most counterintuitive results in all of sea level research. If you're interested in how sea level evolved in the 20th century, what you do is you go around and you look at what's known as tide gauge data. I talked about this a little yesterday. Tide gauges are low-tech devices in our satellite age, where we're now measuring sea level using altimetry. Tide gauges have been out there for, in some cases, hundreds of years. In Scandinavia, the oldest tide gauge is 300 years old. They were, of course, interested in the way shorelines were migrating because of the ice age. These are sort of cylinders. You have a float in that cylinder. As water goes up and down, so does the float. You just have to record the float's level, and you do that continuously for hundreds of years in some cases, and you measure long-term trends in sea level. And if you do that, you get variations like this one. In fact, there are 2,000 tide gauges in use around the world, and one of the things that always makes me pause for thought is that estimates of 20th century global sea level rise based on tide gauge data are generally based on 24 tide gauge sites out of the 2,000. So there is an extensive culling, and there are very valid questions that are raised as to the objectivity of that culling. But nevertheless, these are, just to show you a proof of concept here, I've used the 24 most widely cited tide gauges around the world. They're not binned in any specific order. These are sites in Europe. These are sites in western United States. We see San Francisco, of course. It wouldn't be in San Francisco. One place you avoid to collect, some ways that these tide gauge sites are culled are, you certainly stay away from sites near cities because of groundwater pumping you're going to cause subsidence, right? You also want tide gauges that have had records for at least 30 or 40 years because there are clear and sometimes unexplained decadal trends in sea level. So if you want the long-term trend, you need minimum 30 to, some say 50 years, right? And the final thing you do, and it's a surprise to me to say this, is you try to avoid tide gauges close to tectonic boundaries because of tectonic deformation. So you might ask, why San Francisco? Well, in this particular set of tide gauges, developed by this fellow, Bruce Douglas, who worked at NOAA, by the way, I think for many years, he argued that in transform environments, that is, in environments like we are here, where one plate is sliding as a transform fault against the other, that wouldn't lead to a lot of vertical motion. That's actually not correct. It turns out that my master's thesis was all about how transform motion produces vertical. Transform faults have significant vertical motion on them. Sorry, I'm dry because I'm using decongestants. The air must be a little bit... Yeah, I'll explain. So this scale here is in millimeters per year of this long-term trend at these sites. So you can see that at some sites, carefully culled sites, you would estimate, taking a look at this San Francisco tide gauge, that over the 20th century, the sea level rise was about 0.8 millimeters per year. If you use a slightly better data set, and I checked before I came here, it's sort of 0.6, 0.5 millimeters per year. But at other sites, you've got sea level rise, for example, here in Pensacola, so this would be a Florida site, sea level rise in excess of 2 millimeters per year. Okay? And this was a puzzle, and as I talked about yesterday, this drove a lot of the climate change denying websites. They said, well, why isn't this uniform? If you melt an ice sheet, why isn't it all just going up uniformly? This variability itself was used as an argument against the fact that ice sheets were melting. Okay? And there is significant variability here. And what's typically done, or what was typically done until an embarrassingly few years ago, is you would just simply take the average, assuming in some way that that variability was just random error associated with the measurement, right? Even though there was no evidence whatsoever that that was random error. All right, so what's wrong with this idea of taking the average? Well, underlying that is a sense or a belief that sea level will rise uniformly if you melt an ice sheet. This is my conception of an ice sheet, right? So this is a low complexity ice sheet model, right? So you have a parabola here. It melts down. You would have rise sea level more or less uniformly. The sort of bathtub model, as we say, right? This is not even close to correct, right? In fact, the model is surprisingly counterintuitive. It turns out, as I'll show you, that if an ice sheet rapidly melts, sea level falls dramatically at the edge of the ice sheet. It falls. It doesn't rise. Okay? And I'll explain why that is. An ice sheet, like the sun and the moon, produces a gravitational pull on water, and it brings water towards it. Right? Of course, it doesn't have the time scale of a tide because it's always there. But it's still called a tide. Right? As that ice sheet melts, two things happen. One of that is you certainly dump water into the ocean. You increase the volume of ocean. But you also relax the gravitational tide. Water moves away from the ice sheet. And close to the ice sheet, and I'll define what that means, that tidal effect wins, and sea level falls. It's really counterintuitive. And as I was saying yesterday in my talk, if you melted the entire Greenland ice sheet tomorrow, you should raise globally average sea level by 7 meters, right? But sea level would fall at the margin of Greenland by over 100 meters, right? The effect is an order of magnitude higher than the global average. It's hard to believe, and I do lots, as we've been talking about, Bill and I, of modeling in which we have multiple parameters to tune. There's no parameter to tune here, right? This is Newton's law, right? This isn't a complex calculation in many ways. And I might say that in digging through the literature to look at whether this had been understood, we did find a paper from 1896, a geological survey. A USGS employee was looking at the way sediments would change the height of water and tweaked to this idea of a gravitational pull, right? But long forgotten, and in fact, it was forgotten in the sea level community. Invariably, what people would do is they would see this variability in the data, and they would say, there's a signal back there, it might be an ice age signal. We'll correct for that, and typically you'd see a quote in those papers saying, we want to correct it for so as to have a uniform residual that we associate with present-day melting. Okay? All right, so here's an example. Unfortunately, the colors are a bit dark here, but nevertheless, that's fine. what we're doing is a simple experiment where we're taking Greenland, we're melting enough off Greenland to raise globally average sea level 1 meter. In the sea level world, that's called eustatic sea level of 1 meter. And I've forgotten already to talk to you about how we define sea level. People in the sea level community define sea level as the height of the sea surface relative to the sea bottom. If you're looking at a satellite measuring just the sea surface, you call that sea surface height. Sea level is the difference between those two heights. So you can change sea level both by changing the sea surface or by changing the solid surface. And the reason we define it that way is that geology defines it that way. If a shoreline changes its position, that's either because the land has moved or the sea surface has moved. So for some people, certainly when I speak in oceanography departments, it's a very confusing issue. They would never define sea level that way. But as geophysicists working next to geologists, we do. So here's a map of Newton's law applied to this problem. We melt off enough to raise sea level a meter. This is the actual variation. This blue zone here is the zone in which sea level drops. It's sort of saturated on this color plot. As I said, per meter, you would probably get 20 meters of sea level fall on the margin. So this is a very deep well here, right? You have to go 2,000 kilometers away before you reach the area of sea level rise, right? So if you had a friend and knew that the Greenland ice sheet was going to catastrophically collapse, and I'm a Canadian, so my friend might be in Newfoundland, I might call him to get him into a panic, but he shouldn't be concerned. Well, of course, he should be that the Greenland ice sheet's going to collapse, but his property values aren't going to be affected necessarily from that because sea level will fall in Newfoundland. It'll fall in Scotland. It'll fall in Ireland. It'll fall in Norway and Sweden, etc., right? That's the pattern, but you pay the price somewhere, right, for this, and you pay the price the further you are away from the ice sheet. Sea level will rise 30 or 40% higher. This is, of course, a Mercator projection, which is exaggerating the size of this, right, relative to the equator. But you have to balance. The average of all of those colors over the oceans is 1 meter. So to balance this, you have about a 30 or 40% increase in sea level relative to this eustatic value. I gave a talk at NSF a few weeks ago and had a little bit of fun with it because one of the questions they asked me was, what happens if the West Antarctic melts catastrophically? And I'll show you an image of that in a minute. It had to be done slightly differently because they were asking, what if it all went away rather than you just took ice off? It turns out, lo and behold, the peak sea level rise is just off the coast of Washington, D.C. Right? So it was a nice thing to point out to them. A politician in Boston once said, all politics is local, so I guess all climate change boils down to local, right? Here are the images that come from melting different melting scenarios. This is Greenland, this is the Antarctic, and this is just the global inventory of mountain glaciers, right? So here's what I've already showed you. This is the Antarctic. Melting off the Antarctic, you would have this rim around the Antarctic of sea level fall, and you would increase as you move to more northern latitudes, right? Around each one of the main melting centers, Alaska, Patagonia, etc., Iceland, you would get this deep well of sea level fall. And I mentioned an anecdote, which is actually quite an interesting one yesterday, where there was a New York Times cover article about 7, 8 years ago pointing out that fishermen were skeptical of the idea of climate change in Alaska because they saw sea level falling, right? And they were seeing the Alaskan ice sheets melting. And that's now a well-documented effect. Using Grace gravity analysis, you see this well off of Alaska. Sea level is falling because of the accentuated melting of the Alaskan glacier system. Right? Now, each of these patterns is dependent on the ice sheet. Each ice sheet will have its own pattern, and therefore those patterns now in this game have come to be known as fingerprints. So now, in a matter of 5 or 6 years, the focus of modern sea level research has gone from what's the globally average value, what's that line, to where's it coming from. Because this variability tells you something about the source. If you have enough good measurements, you can extract source information. And from my perspective, that's a more important thing to look at, right? Certainly, nobody disagrees, nobody that's anybody but the most fringe scientists would disagree that 20th century sea level rose 1.5 to 2.5 millimeters per year in that range. It's closer to 2, actually, but that range might be acceptable. Nobody's denying that anymore, I hope. But this gives you a way to move forward. And just to show you, this is not a unique calculation, but just to show you, let's look at that variability again. Now let's ask, can we add up those ice sheet fingerprints that I showed you and match that variability? In fact, there's no problem to do that, right? So that variability is telling you something with source. That's better than 99% statistical significance, fit, improved over just taking the average, right? Okay? This is non-unique for a very important reason, and that is there's a fingerprint missing from this analysis, and that's a fingerprint of thermal expansion. Okay? As climates warm, the ocean is expanding on average, right? And that signal is not known to the accuracy that these fingerprints are known. People are dropping, there's this Argo campaign that some of you may know a lot more about than I do, where these things are being basically sounders. They dropped into the ocean, they measure temperature on the way down, and they're trying to do this. But it's very hard to do that accurately. The thermal expansion coefficient of water changes near freezing quite dramatically. And in addition to that is you may be only 50 kilometers away from where there's a tide gauge, and you think that you're going to get the local thermal expansion, but not even close, right? Near shores, right, the thermal expansion pattern can change dramatically from off the shelf, right? So you really have to have incredible coverage to get the thermal expansion fingerprint. I want to show you, though, I think the most successful application to date of fingerprints, and it's not the modern, although it will eventually be the modern, right? And that comes in the paleo. So I'm going to give you an example of where these fingerprint ideas has helped to, well, I would have said about a year ago, resolve. Now it's a contention has arisen again, but it certainly provided a framework for resolving one of the most important debates in Ice Age climate, right? And that is what's known as Meltwater Pulse 1A. So, sounds like rain. Okay, so 14,000 years ago, sea level rose dramatically. It rose about 20 meters. Some now, recent estimates put it at 15 meters in about 200 years or less. That's sort of an upper bound value, right? That rate of sea level rise is about 20 to 30 times present day rates. In some sense, that's not that surprising. There was a lot more ice around 14,000 years ago to melt, and you are going through a deglaciation phase where all of those feedbacks will at play to cause catastrophic collapse. But what's surprising from anybody's perspective is this most dramatic of all events during the last deglaciation, and there is no consensus on where that meltwater came from. The ice sheet that produced Meltwater Pulse 1A is still unclear. Some scenarios for it have been rejected, and I'll show you why that is. Unfortunately, I didn't update this slide. There's much more data here that would convince you more than this figure does. But the red and the blue here represent data sets coming from two different places, Sunda Shelf in Vietnam and Barbados, which is always central to any discussion of Ice Age climate and Ice Age sea level, right? And if I showed you the full data set or the original papers, what they both concluded, although there may be a social scientific description for this, people tend to jump on bandwagons here. The people who did Sunda knew what the analysis in Barbados had shown, and I can't suggest that they were biased, but you never know. They argued that the jump in sea level at Sunda was precisely the same as it was at Barbados, right? And that's still, people have looked at that data independently, still believe that that's true, right? Okay, from simple fingerprint ideas, that tells you that this here lies a mechanism for at least rejecting some hypotheses for where that meltwater comes from, right? And for example, I forgot to make one small point, which I think is important here. When I showed you this modern sea level, and this has been known for 50 years, that European sea level measurements in the 20th century show lower rates than everywhere else. And just from this simple fingerprint physics, you realize why. That means Greenland was melting in the 20th century, because Greenland would produce a lower sea level rise in Europe than it would globally. In the same way, we now see measurements at Sunda and at Barbados, which tell us that at Meltwater Pulse 1A jump was the same in both. This is just it's more for my benefit than yours, but for me it sort of summarizes where people thought Meltwater Pulse 1A might come from. The consensus view prior to fingerprinting work was it came from the southern sector of the Laurentian ice sheet. right? And in many ways, there's really no clear on-the-ground evidence. No geologist I've talked to would suggest that there was a change in the moraines here at that time of such dramatic extent. To get 20 meters, you would have had to melt the whole southern sector of the Laurentide ice sheet, right? The reason people point to Laurentide is maybe a logical one. It was by far the biggest ice sheet. Where are you going to get the 20 meters? That's the way the logic prevails, right? Another reason that it was thought to be the southern sector is if you melt you melt ice sheets and you throw meltwater into the ocean, you're going to produce oxygen isotope anomalies, right? No anomalies were seen in the St. Lawrence or in the Arctic outlets for the Laurentide ice sheet, dated to this time period, but there were some anomalies seen in the Gulf of Mexico, dated to meltwater pulse 1A. Recent work, 3 papers in the last year, though, have shown that that Delta 18O anomaly can be explained by 1 to 2 meters of melting from the southern sector, not the 20 that you would need to explain meltwater pulse 1A. Others have argued that, oh, well, maybe it came from Scandinavian ice sheet or the Barents Sea. Perhaps a contribution, but the net ice volume in the Fennoscandian ice sheet was probably on the order of 10 meters. And where are you going to get the 20? Other people pointed to the Antarctic. And this is not atypical, and I must say that I pointed to the Antarctic, but it's not an atypical story in Ice Age work. When you don't know where it comes from, throw it in the Antarctic, because the constraints are the least robust there. That's just the way it is, right? So in 2002, I threw it in the Antarctic, right? There were some suggestions of isotope anomalies, but what I certainly believe, and what I think is now well established, is it could not have come solely from the southern sector of Laurentia, and here's why. Here are fingerprints for that event. This is a fingerprint of melting from the southern sector of the Laurentian ice sheet, this blue region. These are papers over several years, so it's a dark blue here that represents the region of sea level fall, surrounded here by progressively increasing sea level rise. But there's Barbados, and there's Sunda Shelf. If you melted from the southern sector of the Laurentian ice sheet, you would predict a sea level rise at Sunda Shelf which is 65 to 70% bigger than Barbados. That's not what's seen. That can be ruled out. One of the intriguing issues when it came to the Antarctic was a West Antarctic source produces the same sea level rise at those two sites, right? The problem with this story, which sort of held up for 3 or 4 years, is that more and more modelers of the Antarctic ice complex from LGM onwards, that is, jargon from last glacial maximum 20,000 years ago onward, are now lowering estimates of the ice volume at last glacial maximum. The current estimates of the Antarctic ice volume at last glacial maximum relative today, if you took the difference, spread it out over the ocean, is 7 to 8 meters. In the time that these papers were being written, it was 20 to 25 meters. So now ice sheet modeling is saying, and I'm somewhat skeptical of this modeling, saying, no, we can't get an ice sheet any bigger than that over the Antarctic. So people are looking for other scenarios, most of which can be rejected. But there's one that was published last month that cannot be and deserves closer thing. And unfortunately, it's hard to see here. But this was a paper published by Laurent Gredoire at Bristol. What she argued was that you had the Laurentide and the Cordilleran ice sheet that existed at this time, and you had a saddle of ice that connected to them. That saddle collapsed 14,000 years ago. And her argument was that that could be a source of meltwater pulse 1A. And when you do the fingerprint, it fits. Okay? It fits the Sunda data and it fits the Barbados data, the equivalence of the observed sea level rise. So this is a possibility that deserves more work. I spoke to a very well-regarded paleoclimatologist in France, Edouard Bard, who may be familiar to some of you here. And he showed me, he sent out a proposal to do drilling off Tahiti, which has now been done. And he said, we need a measurement of the meltwater pulse 1A sea level jump in Tahiti. And it was rejected by every single reviewer who said, we already have one in Barbados. Why do you need another one, right? So he resubmitted saying, this is why. You need more. You need geographical coverage before you can source these things, right? One is not good enough, right? And the more you have, the better. And in fact, I allude to that. This paper was just published by Bard and his colleagues in Nature 3 or 4 months ago, actually, which also argued, based on the Tahiti site, that it seemed to be sourced to the Antarctic. So this is a lively game again, and it's interesting to follow it because there's going to be a lot of work in the next few years in resolving it, right? One can't imagine a more important sort of ice age climate question in some sense, right? Okay. Now I want to talk about some things that, in some ways, I'm going to admit to being just a puppet here. This is my graduate student's work, right? And she's done something really remarkable. Her name is Natalia Gomez. And what she did is she went to the ice community and said, how are you modeling sea level in your models, right? And they told her that typically what's done in sort of ice sheet reconstructions or ice sheet climate models is that if an ice sheet melts, either nothing happens to sea level or it rises. With her understanding, of course, that if an ice sheet melts, sea level falls at the margin of that ice sheet, she understood that that should have significant impact on the stability of that ice sheet. There should be a feedback, right? And there is, and it's a significant feedback, and I want to show you some of her results. But these are all her results, working in particular with Dave Pollard, who's a climate modeler at Penn State, right? So let's step back and look at this historically for a bit. This is probably the most famous of all papers, early papers in ice sheet. And I should say here, where I'm really focusing here on marine ice sheet stability. So I'm going to be talking about the West Antarctic ice sheet. That is, these are ice sheets in which the bedrock is below present sea level. If the ice sheet wasn't there, you'd have ocean. Okay? The West Antarctic ice sheet is 60 to 70% a marine-based ice sheet. Okay? And thus, as the saying goes, it should be inherently unstable, and it is. That's not going to change. But one has to quantify instability, right? So here's a cross-section of the West Antarctic ice sheet in an interesting area because GRACE satellite gravity, recent GRACE satellite gravity images show this is the hotspot in the West Antarctic now. This is where most of the mass loss is currently occurring in the West Antarctic. And it's over the so-called Pine Island Glacier, right, which is just to the side here. This is actually a cross-section to something called the Thwaites Glacier. I think that's how you pronounce it. Okay, what did Wortman do? Wortman's analysis, and I'll show you just one figure from it, has set up a sort of mantra in marine ice sheet modeling. And that is, if an ice sheet sits on bedrock that slopes downwards towards the center of the ice sheet, it's inherently unstable. There will be catastrophic collapse, right? The idea is you have ice flux through the grounding line, at the grounding line, the margin. If you were to melt this back a little bit, because you're deepening, you would increase the amount of ice flux out of the marine ice sheet. You would reduce the accumulation of mass because you're shrinking the size of the ice sheet. And by doing that, you set up this feedback that will just lead to catastrophic collapse. Okay? That's the idea. Here's a kind of quantification of that, a very simple one, but an elegant one. The Wortman paper is just an unbelievably elegant mathematical analysis. Although you have to look at it for 6 months to realize it. It's one of these papers that's quite opaque. And then you say, aha, 6 months later. Okay? But this is his analysis, right? He looked at the critical bed slope, that is this bed slope that would lead to instability, as a function of the ice sheet radius. And he found that there was a sensitivity, but the important thing is that any negative bed slope, anything, no matter what the size of the ice sheet, that asymptotes to a value above 0. And if it doesn't, it's because it's plotted incorrectly. No, it does. Any ice sheet sitting on a negative bed slope is inherently unstable, according to the Wortman analysis. Now, this analysis was an equilibrium, or what we call in the sea level game, a static analysis. There's no time dependence here. He wasn't analyzing the time scale at which this happened. He just said, I'm looking at an ice sheet, what will happen over infinite time to that ice sheet, right? And so the first thing Natalia did was she reanalyzed this, taking into account the fact that as that ice sheet retreats, sea level will fall here, right? And because it falls here, of course, it changes the amount of mass flux from the ice sheet into the shelf, right? And here's the first redone static analysis or equilibrium analysis. The instability drops here, so you can have many ice sheets of many different bed slopes that are negative that are in fact stable, right? So this is no longer universally true, right? And I think it's now widely understood in this community that marine-based ice sheets with negative slopes can be stable, right? Not too negative, of course. And I'll quantify what that means, right? So this was the first indication that the Wortman ideas needed revision to take into account sea level. So here's the next step. You go from a static theory now to an analysis in 1D, a one-dimensional ice sheet model in which you incorporate all of this physics and you evolve the system through time, where you're looking at the time scale. And Bill and I are both a little nervous because I have a film in here that seems to randomly work, right? Okay, here's how they set up the model. I don't know if many of you are familiar with this. Well, certainly it includes all the sea level stuff that I've talked about. This gravitational self-consistency I was talking about, that the movement of water deforms the Earth. It has a direct gravitational effect and a deformational effect on the gravity field, etc. The deformation is now viscoelastic. The evolution that I'll talk to you about is over many thousands of years. You can no longer assume that the Earth adjusts elastically. You have to include the full viscoelastic effects. But from a dynamic ice sheet model perspective, something I know a lot less of, we're using the 1D version of Pollard and DeConto's model that they published in Nature. I guess the main thing is it's really just an ice sheet, ice shelf model, and it uses parameterization of ice flux across the grounding line here that was described by Schoof in a paper about 5 or 6 years old now. It's very well cited in the literature. Okay, what happens? We're about to see, if we'll know what happens, right? Here's the setup of the model. We've just set up, because it's a 1D model, it's azimuthally symmetric, we set up a disk of ice that has the same net area as the West Antarctic. Over the pole, we have a global ocean that covers 70% of the Earth's surface, as does our ocean. This is a 1D model. You set things up here, and you perturb the system. Here's an ice sheet with a radius of around 1,000 kilometers. You've got the shelf out there, and now you just perturb this system. You do something to perturb it. In the cases that I'm going to show you, although Natalia didn't answer my email this morning, I believe what they did is they just lowered side friction to allow the thing to move. So, and the other way you could do it, of course, is just add some temperature, right? But they just lowered the sidewall friction, right? And you may ask how you do that in a one-dimensional Earth model, and that would be a valid question, right? Okay. This is just to say that most ice sheet models, and this may be a subtle point, but one that some of you have much more experience than I do, typically fix the sea surface height, right? And as I was telling you, sea level changes, and I didn't tell you part of the story because of this gravitational effect, the water sea surface lowers, but what I didn't tell you, and I should have, and I forgot, was that the land also pops up at that same point, right? So those two surfaces change. In order to implement that physics into a code that keeps a constant sea surface, you apply the entire sea level change to the bottom bounding surface, right? And in talking to ice sheet models, Natalia has found that that's important to emphasize. Because this issue of what is sea level really becomes a tricky question, right? Okay, shall we try this? Bill? Okay, so this is going to be a model of the evolution of that ice sheet when it's placed on a bed with a relatively high bed slope, okay? You saw it work the last time. Okay, but we have a fallback, which is we have another one waiting here, right? Let's hope. If this doesn't work, then, oh, please, yes. It's one of those moments in a talk where you think, thank God. Okay, but I shouldn't celebrate too early, should I? Okay, so here it is on a very large bed slope, right? And what you see here, I'm sorry, and I hope I can keep repeating this, this is with the feedback that I've talked. No, this is no sea level. I think she's gotten those confused. Let's do it again, though. Oh, no, she hasn't, of course. That's, this one, which is slowed down, yes, she has the sea level feedback that I was talking about, right? So there is a clear change in the time scale of that. She probably just did that to keep me awake. Okay? Let's just one more time. Here's the evolution of that marine ice sheet. It's being slowed by the coupling. The other one's gone. In this particular case, the time scale for collapse is increased by a factor of 2. So now let's look at another case, try my luck here, where it's on a much more gentle slope. And in this case, you'll see that the coupling means that the ice sheet it reaches another steady state and doesn't fully collapse, right? Okay. Again, the coupling is on the bottom one here. This is the one that doesn't include the coupling. This is going to collapse in about 7,000 years, and that reaches another steady state in just after 10,000 years. So depending on the slope, you can not only increase the time scale of collapse, you can stop the collapse altogether. All right. So let me go now back to the... That wasn't too painful. It was going to be worse. Okay, this is a diagram that she put together just to summarize a bunch of these 1D runs. What she's done is she's plotted against reverse bed slope here and the reduction in the forcing. So by what extent did she remove this sidewall friction, right? From 0 to 100%. And what this is, it's a bit complicated, but it is the factor over which you increase the time scale of the collapse to 500 kilometers, right, by incorporating the coupling, right? So value of 2 there means that when you included the sea level coupling, the collapse of the ice sheet down to a 500-kilometer radius took twice the time without the coupling, right? And not surprisingly, if you have a high bed slope and a very strong forcing, you're up here, and the time scale isn't changed much at all. But as you decrease the bed slope or decrease the forcing, the importance of this coupling increases. And in fact, this region here is the region in which it just stops at another steady state, right? So this is a sensitivity study, but you can see that over plausible ranges, I can't speak to the plausibility of that forcing, but over plausible ranges of bed slope in the present-day West Antarctic ice sheet, you would have a significant effect on the evolution of that ice sheet. Let me show you just a couple of examples now of a 3D simulation. So these are just being done now, right? Where she's taken the entire Antarctic ice sheet, run it through this Pollard and contour model from about 50,000 years ago to present day. She's looking at the ice age again. You have to go to 50 because you need it to wind up a little bit. And she's looking from LGM to the modern, the evolution of that ice sheet. And here, things get very complicated in some ways. But I wanted to, even for me, I'm looking at these for the first time, but I wanted to show you some of these. These were done last week, okay? These are just plots she put together to say we're coupling this ice evolution with the global sea level calculation, right? And doing it totally in a global context. Up till now, we've just looked at the Antarctic. From 20,000 years ago to 5,000 years ago, a lot of ice melted in the northern hemisphere, and that is included in this model. So that ice is melting, and the sea level change it produces in the Antarctic is being incorporated into the simulation. And there's lots of reasons to do that that haven't yet been explored. Lots of discussions about hemispheric connections between ice sheets, etc. Did the north lag or lead the south, etc.? It's these kinds of models that are going to try to tease that information out. You don't want to not include, doing an LGM to present day run, you need to include the entire ice inventory, right? Okay, here are just some snapshots now. It depends on how you run these models. You start at the same point 50,000 years ago, so out here, you run them. In this particular case, and I don't know the full details of the forcing, you have just what you think to be a reasonable climate forcing that's applied to both of them, right? And then you evolve through time to the present day. Because you've done nothing to tune at the present day, they will evolve to different points in the present day. But at some level, we could stop by just looking at the difference in this magnitude of the red versus the green. Because the red includes the coupling. And from the physics I've talked to you about before, it's not surprising that the total magnitude of the change in the Antarctic ice sheet is diminished considerably when you do that. But the time history is a more complicated issue, right? If we look at sort of 12,000 years ago, there are fundamental differences in the size of the West Antarctic ice sheet. Here's with the coupled model, you still have very significant ice cover, probably a lot of it grounded over what is present-day shelf. And here in the uncoupled model, the original. And I'll just run through some of these because I think they're interesting to see. Here is taking the present-day view of that. Even at the present day, you'd have significant differences between that evolution. This is really just to reinforce the idea that there's an important physics here. This is a different experiment now. This is an experiment in which both the coupled model and the non-coupled model are both tuned independently to reach the same present-day condition, the modern, right? And so we're all the same here because you're tuned to be the same. The question is, let's look at a kind of meltwater pulse 1A time, 12,000 or 14,000 years ago. And the difference in the evolution of the models is significant, right? Only to say that this is the first calculations from the 3D code. This is a physics that you want to incorporate in these codes, right? I'll just follow this on a little bit because as an Ice Age sea level person, the first question I had for Natalia was, well, okay, these are interesting, but do they come even close to fitting Ice Age data sets like relative sea level curves that have been developed around the Antarctic margin, right? And so she looked at that. This is just to set up the next slide, but, and the colors are different on my plot, but very similar on this. That's actually green on my plot, right? But anyway, luckily there's also a thickened line here. This is just at a particular site. This is over the time scale of the last 12,000 years. This is the predicted sea level change, or relative sea level change. That relative means that it goes through zero at the modern, right? And the coupled versus the uncoupled model, right, have very significant differences. If you predict different ice volumes, you're going to predict different relative sea level histories. There's a strong deformational effect here. So now let's look at sea level sites all around the coast of the Antarctic. And when you do that, I don't know how I did that. Some things are working even better than I prepared, right? As you go around here, you see a consistently better fit with the coupled model, right? There was no tuning here at all, right, to sort of fit relative sea level curves, right? You just switched on something that well, there was a tuning to get to the modern condition, the modern extent of the Antarctic ice sheet, and then you either switched on or off this coupling, and that's what you see. And you can see that getting to the modern can produce very different sea level histories at these sites. And so that's obviously another constraint that ice models for this region need to bring to bear. But in general, this is looking, you can be optimistic that we're moving in the right direction, right? There's another data set here. Apparently, there's all sorts of GPS installations on the Antarctic. And what Natalia's done here is to look at those sites in which there are measurements of GPS, present-day vertical rates of change of the crust due to Antarctic melt. Here is the no coupling. Oh, no, that is the coupling. This is the model that has no coupling. The argument is there's a better fit. GPS data are notoriously difficult to fit because it turns out that sort of present-day rates of change of crustal motions are very sensitive to slight heterogeneities in the crust, right? But nevertheless, this is hardly an exciting fit, but it's certainly better than one that shows no fit whatsoever, right? Okay, so these are the sort of the conclusions, and I have a few minutes, 15 minutes, so I'll use it for the next part of the talk. But certainly, in modern sea level research, the main motivation of modern sea level research now is to fingerprint the sources of meltwater. That's true whether you're looking at sea level or any other sort of geophysical signal associated with that melting. We were talking at dinner yesterday about a young scientist, Mark Tamassi, who's at Proudman Institute of Oceanography, I think, in Liverpool. And he's pointed out something quite interesting, and it's a way to get around this thermal expansion problem that I was talking about. And I wish I had thought of it first, right? But what he showed was, yes, Mitrovica is saying you can't do this because thermal expansion kills you. We need the thermal expansion map. What he's done is he's argued, no, you don't. We'll go to the ocean bottom. We'll put ocean bottom pressure gauges there. Pressure won't be influenced whatsoever by thermal expansion, right? But it will be influenced by true sea level change, right? Changes in volume. So it's ingenious because it gets around the problem of needing the thermal expansion field. Of course, not cheap to put these things down there, but really well worth it because I think that's the best hope these days of fingerprinting sources for modern sea level, right? Just a great idea. He was a former postdoc. I should take some credit. But none at all. I would never have thought of it, to be honest. Right? I wanted to emphasize with you that these fingerprint ideas aren't simply a modern phenomenon. There's lots of applications to paleoclimate research. If there's one, when I was a graduate student, I used to draw the ice age ice volume change as what we call the sawtooth. Nice gradual increase, collapse. Nice gradual increase. You draw this figure. And I remember drawing it as a graduate student and you know, having the two lines, AX plus B, set up, right? But what we know now is that the ice age wasn't like that. You certainly didn't go gently out of the ice age in the last deglaciation event, right? We had Meltwater Pulse 1A, we had the Younger Dryas, we had all sorts of really cataclysmic swings in climate. And as we understand that more and more, we were talking at dinner tonight, for example, even in the inception of the last glaciation, 10,000 years into the last glaciation, about 100,000 years ago, an oscillation in ice volume of about half the total oscillation from LGM to present is thought to have occurred over 10,000 years. What is driving that, right? Well, if you have enough sea level data points from that time period, you can fingerprint them. And finally, this issue, which is probably the most important for this audience, is that this physics is really an important ingredient to incorporate into modern computer simulations of ice sheet stability. I wanted to talk just a few minutes about one paleo study that I focused on yesterday down the hill. So those of you who were there, I apologize. It turns out, become quite interested in what I might call ice age warm periods, interglacials, right? I really do subscribe to the idea that one way to assess where we're headed in this progressively warming world of ours is to look at the last times in Earth history that we had that level of warmth, right? And so I've written a series of papers recently on interglacials and on the stability of ice sheets during interglacials. And I want to show a paper that was just published that looked at one specific interglacial called MIS11, 400,000 years ago, 4 interglacials ago. And I'll go through a summary of why that's important in a minute. But it was an interglacial in which we basically reached temperatures that we're about to reach. And we stayed there for a number of thousands of years, right? What happened to the ice sheet there is a huge debate. And I want to show you there why these same arguments of the geometric variation in sea level becomes absolutely vital to understanding ice sheet stability during those periods. But to do that, I'm going to give you I've just shown this is an oxygen isotope curve by Lasicki and Ramo, just a stack of many of these curves back from the last 3,000 years. And there's MIS11. So we go through another 4 ice age cycles before we get to today. And that's the target here, right? Okay, and I won't go into detail, but you know from oxygen isotopes, this is when ice volumes are high, this is when ice volumes are low. And I must say, and this is just an editorial, that this argument of being able to scale from oxygen isotopes to sea level is madness, right? Okay, I don't believe it. Anytime I've had good enough data to check specific time windows, it's not even close to being correct. So on a general level, you can do this. You know you're in glacial maxima here. You know you're in glacial minimum here. But to use these curves to show you the trajectory of ice volumes is not, I think, in my view, and you should get people in here that disagree with me, a robust way to look at ice volumes. Right? Certainly not through periods like Meltwater Pulse 1A. I'll focus on this one slide for the next 3 or 4 minutes because this is a prediction of how sea level will change through an interglacial. That is, there is no change in ice volume in this model. This is a numerical prediction. We go through the 100,000 year cycle. This could be today's interglacial or 400,000 years ago interglacial. The picture would be roughly the same. Certainly would change depending on the geometry of the ice melting that preceded it, right? But this is a typical map you see. This is taken from an old paper by a graduate student of mine that was focused largely on the far field of the ice sheets. And so this color bar here saturates in the near field, right? But I'll try to go through this physics. Sorry. Okay. Oh, that's unfortunate. Don't worry about that. Apple has assured me that that can be fixed, right? And that's what went wrong yesterday. Somebody at Apple, we were having trouble with this figure, said, oh, no, you'll be fine. Safe reboot. For those of you who know what a safe reboot is, I'd never heard of it before, right? So I did, and all my movies disappeared. So one person's definition of safe is not another's, right? So this is a sea level change that you predict to occur through an interglacial period. And this includes full viscoelasticity. This is not the fingerprints I showed you before, which is this rapid event. This is what's continuing to happen today, 5,000 years after the major late Pleistocene ice sheets melted away. In a sense, this is largely viscous, not elastic. Okay? And I just want to show you generally what this is all about. This is fundamentally important in studies of modern sea level. And the reason is, if you go around to those tide gauge records that I talked about, the first thing you have to do, you have to correct for this. You have to correct for what the ice age is currently doing to sea level, because this has nothing to do with ice volume. If you don't correct for this, you go wildly wrong in those estimates, right? So it's important from that perspective. But let me get on with this and try to describe some of the physics. In the near field of the ice sheet, so let's focus on Hudson Bay, for example, or on Canada. Here you had the Laurentide, Cordilleran ice sheet, and that saddle that I talked about earlier between the two. From 20 to 5,000 years ago, that melted away, right? As it melted away, the land began to rebound, right? And you've probably all heard the term post-glacial rebound, right? So the land began to uplift. And remember, I said that sea level is the difference in the sea surface height and the land surface. If that uplifts, what you will see is a sea level fall, by my definition. Of course, if you're looking at a satellite, you may see something very different, right? But looking at geological records of sea level change, you see a sea level fall. And that's what's predicted in this model. This deep red is actually way down there, because this is in millimeters per year, and the sea level fall presently in Hudson Bay is about 1 centimeter per year, right? Okay? Surrounding these regions are what are called the peripheral bulges. So you have this big depression where the ice sheet used to be that's coming up, and we can track that progression using gray satellite gravity as well. Around it are peripheral bulges, zones in which, as this went down, they came up. You have to conserve mass. So when this is coming up, when this is post-glacial rebounding, those bulges are subsiding. And in those regions, because of subsidence, you're increasing sea level. This is a region of sea level rise that reaches, on the U.S. East Coast, 2 or 3 millimeters per year. And this is something I mentioned yesterday. But just, we could stop right here, and I could say, you know, if you had a tide gauge record there, and you saw 6 millimeters per year of sea level rise, and you associated it all with ice melting, you'd be wrong by a factor of 2, because you have to take out this effect, this ongoing adjustment that produces along both coasts of the United States a sea level fall, a sea level rise, sorry. Okay? So those are those two effects, and I'll show you just a figure of that. These are, oh, those are way too dark to see, but this is a very classic picture, if you saw it, of what's known as flight of raised beach terraces. So the great Canadian and American geologists used to go to these areas and map these old beaches. You see a beach, the land keeps hopping up, the next beach forms, and the next beach forms, and the next beach forms. That's a continuous process, but it is thought, and Bill Dietrich has told me to be skeptical of this idea down the hill, that you get discrete beaches because of discrete storms, right? But you get this beach line. You just date organic material across there, you get a height versus age curve, and you get a sea level curve, right? And this is a picture from Greenland, which also you can't see. But what about this far field area? What about this blue? Because I've spent a lot of my time working on sea level in what I would call the equatorial Pacific. Having been born in Australia, that's a bias. Okay, I'll just focus on one aspect of this. It's this sort of yellow-orange here. What this is telling you is that because of the ice age, if you're in the equatorial Pacific, and I'm going to show you a photograph from that point right there, Malden Island, sea level should be falling 0.5 millimeter per year. Okay? You're in an interglacial because of this effect. You'd have to superimpose a modern climate change effect on it, right? But if we go back several thousand years, that 0.5 millimeter really adds up, right? Over 5,000 or 6,000 years, that net sea level fall is going to be 3 meters or so. And we only go back 5,000 or 6,000 years ago because prior to that you were melting ice, and so everything was swamped by throwing water into the system. But at 5,000 or 6,000 years ago, that stopped, and this process, whatever it is, I've yet to define it, becomes dominant. And it leads to these features, right? These are pervasive in the equatorial Pacific. They're called 3-meter beaches, 3-meter corals, 3-meter notches. The term is used, right? The top of that coral, which is now dead, well, there's a live coral there, but the top of that coral is 3 meters above present-day sea level. It's dated to 5,000 years, right? Now, these have been certainly known for a lot longer than Ice Age sea level calculations have been done. And the typical explanation for these was that they were driven by thermal tectonics. The crust is moving over an enormously hot region in the mantle, and everything is coming up, right? But that couldn't be the explanation. People knew that that was unsatisfying because these features spread over 10,000 kilometers of the equatorial region, right? Not everything can be coming up coherently over that. It turns out that this is an Ice Age effect, something that you wouldn't blame somebody if they were sunning themselves here from believing that coral exposed is due to the Ice Age. And now let me go back to this physics to tell you why that is. Well, I told you that these blue regions here are regions in which the crust is subsiding, sea level is rising. That means water is entering into those regions. Geologists would say water is entering into the accommodation space that's produced by the subsiding bulges, right? So as those bulges subside, you are migrating water from these regions into those regions to fill that need for water, right? And as you do, it's like this is where an analogy in a bathtub may not be bad. If you have something submerged on one side, let's not say a bathtub, a long swimming pool, you take that thing that's submerged off, you'll see the whole level drop, right? And that's what you're seeing here. You're seeing the whole level drop because water is flooding into these areas, right? Now, why have I talked about all of this? Because of MIS11. That's an interglacial. And I want to talk to you about what is still a very contentious debate based on two observations. 400,000-year-old beaches in Bermuda and the Bahamas are now seen to be 20 meters above present-day sea level. You can go there. They're easy to measure. The fact that they're uplifted, they're well preserved. There's no debate that beaches of MIS11 age now appear 20 meters above sea level. Okay? What does this mean, right? You know, that measurement, does it mean, for example, that you melted enough ice 400,000 years ago during this interglacial to raise global sea level by 20 meters? That would require you melting entirely the West Antarctic ice sheet, Greenland, but also a significant fraction of the East Antarctic ice sheet. Was this protracted warm period a period in which that East Antarctic that we sort of hold on to for its stability, was it a period in which the East Antarctic gave up in some sense, right, and started collapsing, right? Well, that's one idea. Here's a typical data set. Oh, this shows up. That's a coral, actually, believe it or not, all the way up here. Of course, a sequence of corals. And that's a data, I think, in the Bahamas. Yep, there it is. 20 meters above present sea level, right? Dated to 400,000 years. Okay? Here are the two ideas. The one is, yes, there was a collapse of the East Antarctic ice sheet. All right? That's the only way you explain it. The other, and again, we have to drag Bill Dietrich up here to tell us why this is possible, is that a mega tsunami did it. That one of these once-in-a-millennium events swept through, produced a shoreline at this 20 meters of height. And those are the two consensus ideas for this period. And apparently, and I'm not a geomorphologist, but it is difficult to tell a shoreline produced from such a transient event from one that, after all, even if it was a collapse of the Antarctic ice sheet, it didn't last long because you then entered into the next glaciation phase. So was it a tsunami or was it just a short-lived high stand associated with the collapse of the East Antarctic, right? Okay, well, the problem is that none of those analyses took that into account, that there's an ice age signal, right? And so let's take that into account. This is the sea level change that would occur across that interglacial 400,000 years ago with, again, no change in ice volume, right? So I've assumed no change in ice volume. I go through, in this case, an 11,000-year period, which is the best estimate for that period of stability, in which I don't change ice volumes at all. So nothing in this figure is due to changing the mass of the ice. And yet you have these huge changes in sea level because of these adjustments. And I'm going to focus just on Bermuda, which I think is there, and the Bahamas, there, right? Those sites live on the Laurentide peripheral bulge, right? So those sites during an interglacial see a relatively large sea level rise, in fact, a very large sea level rise. The red here says that in those sites, because of this peripheral bulge subsiding all through the interglacial, that net subsidence over an 11,000-year period adds up to about 20 meters, right? And so at the very least, you think some of this has to be taken into account when you're estimating those curves, when you're looking at those curves. And I want to get just to this, which is a prediction. Now, it's slightly misleading what I told you, because that's the total sea level rise across that ancient interglacial. But we've been in an interglacial today for 5,000 or 6,000 years. And sea level has been rising in those same sites because of the current interglacial, right? So really the question is, where is the adjustment today relative to where it was at the end of that interglacial? How much higher did you get there than you've gotten now, right? And it turns out you got about 10 meters higher. If I look out, and there was no change in ice volume, and I look back at Bermuda, and I say, there's the 400,000-year beach, it would be 10 meters higher than present day. But remember, I'm in a peripheral bulge. Sea level is going to continue to rise here. And literally, I am in California, right? Sea level is going to continue to rise here. So as a function of time, that beach elevation is going to come down, and it'll be at zero when that interglacial was the same duration as the present interglacial, right? You've gone up the same amount, right, rather than coming up much less. So you have to correct those data for 10 meters. That 20 meters, half of it is associated with the Ice Age. The other half is associated with melting, right? And these are just predictions of the corrected height, depending on whether that interglacial, the ancient one, was 9,000 or 14,000 years ago. The best estimate is between the two. The residual is 8 to 10 meters. That's not a great conclusion, right? But it is consistent with our understanding of other interglacial. The last interglacial, which is known as marine isotope stage 5E, rather than 11 here, there's now consensus. The first time I've seen this in the sea level literature of interglacial, a whole series of papers have now published that said, eustatic sea level, globally average sea level, 120,000 years ago was 10 meters higher. That means Greenland and the West Antarctic completely collapsed, right? What this is telling you is that the same thing happened at MIS11. Although it's probably true that the East Antarctic survived intact during that interglacial. So that's the one conclusion. I had more paleo stuff, but that's enough for today. Just to give you a sense, as I wrote in my abstract for this talk, that fundamental insight comes through an analysis of the geographic variability at sea level. The minute you take an average, you lose all the information, minus one, right? And so that understanding is really informing studies of modern sea level and paleo sea level now. And I'm hoping by talking to an audience like this that it will also inform models of ice sheet evolution, whether in the past or in the modern. So thank you very much. I'm certainly not one, I'm not the person to look, but there are people looking. And the reason there are people looking is, again, Meltwater Pulse 1A. There's a large group that says, not so fast on the saddle idea. West Antarctic, a significant fraction of that 20 meters might have come from the east. And what people forget is there are sections of the east that are marine-based. They're smaller, but they still account for 5, 6, 7, 8 meters. That's only 10% of the East Antarctic ice sheet, but in terms of volume, it's the same as the West. So all I can say, not being a sort of glacial geologist, is that there are people out there looking. And they're looking now. It's January, right? That's when they're out there, right?
I just want to follow up on that point. I would have thought if there were sufficient core, well, I don't know how many cores there should take around Antarctica. I would think that just by doing cores around this perimeter, I mean, that would be, rather than doing a core in the center, which is what people have been doing to get on record, I would go to the perimeter.
To see what...
I want to know how long that perimeter has been around.
Yeah, but isn't it true? Well, but I thought, and again, this is not my expertise, but I thought that those cores, as you go to, and there are probably experts here, but as you go to the edges of the ice sheet, those cores are deformed significantly by ice flow, right, ice dynamics. But there are certainly people, what they're doing is they're using, I wish I could remember the name, there's a fellow at Berkeley doing this, but by looking at isotopic signatures of being exposed, people are trying to date last times of exposures of these rocks, right? And if you're getting any of it out of the east, you must have, just like in the west, you must have exposed a very significant amount of rock. And that's what people are looking at, rather than cores in the sense you're talking about, Bill.
Other questions?
We were supposed to have a long question period.
Yeah.
Yep. Sorry? Yep. Right, that's the answer. Because some people look at the ice age signal and say, oh, no problem, we're dropping 0.5 millimeter per year. But there's no scenario, and here's why that, let me give you a better answer than just saying yep, and that is, anytime you're relatively close, what's the latitude of the Maldives? Right, so anytime you're near the equator, you don't get any benefit of the fingerprint, right? If it's coming from the north or the south, you're not getting any benefit of that gravitational signal, and so you're getting a double whammy, right? Whereas when I showed those NSF folks the picture showing that peak sea level across the U.S., just offshore Washington, if the West Antarctic melted, they would do better if the Greenland ice sheet melted, of course, right? Because they would get some benefit from that gravitational signature. But if you're on the equator, you don't get any benefit from either. And actually, you get relatively close to within 10% of the eustatic average level. And you know, when I give a public level talk on this, I often focus on the sea level fingerprints as an argument against this argument that variability in sea level it means that it's not coming from ice. The other two things that I look at and show this public audience is one, another typical argument you hear is this has been going on for thousands of years, and there's no difference. And of course that coral I showed you shows that that's a complete lie. If that coral would be under 10 or 15 meters of water if sea level was going up 2 or 3 millimeters per year for the last 5,000 years. But the other thing that the argument goes is that, okay, let's concede that it's going up 1.5 to 2 millimeters per year. It's not going to get worse. But it already has, right? Sea surface height measurements from satellites show that the current globally average sea level rise exceeds 3 millimeters per year, right? So we're already out of that range, of that 20th century range by about 50%. And there are many people here active in the IPCC report, and one of the things people sighed about at the last report was this projection of sea level, because when that IPCC report was published, we were already at the upper bound of sea level change, right? Already, at the time of publication. So I'm not really sure where that uncertainty bound came, given that satellites put us at. So the Maldives are cooked, right? At Greenland. It happens instantly. So the minute, so here's where I should clarify, because my pictures all show the gravitational effect. But right at the margin of Greenland, two things happen, the gravitational effect and the crustal rebound, right? And right at the margin, it's about 50-50. So you lose sea level because of this, equally to that. So the minute you start melting, elastic deformations take place, right? And I mean the minute. The Earth will, we see that in measurements. There is a new paper out on Salt Lake, Great Salt Lake, and as it grows and diminishes seasonally, and crust moves up and down seasonally, precisely modeled as if the Earth was an elastic ball. So these crustal changes, the elastic effects, are effectively instantaneous. No. If the crustal effect, so this gives us 100. So if the crustal effect didn't happen, if it was a rigid Earth, it would be half, 50, right? So, and the topology of that area of sea level fall depends on the scale. So Alaska, for example, has a thin but very deep region of sea level fall. It still goes out 2,000 kilometers, but it has these thin tails to it. And so you really do get these very dramatic drops in sea level. Alaska's probably losing more than any other, I think, glacial ice complex on Earth today. So that's where the effect would be the largest. Right. Yep. Yeah. Oh, yeah. This is a very good point. It's something that we talked about at dinner last night. I'm working with a group that does things called hosing experiments, right? And what they do is they basically put a hose out there and dump fresh water. Many of them aren't. The site of hosing is not well resolved, so they'll put it all in the North Atlantic. So it's another issue I haven't even touched on in modern sea level, but the predictions I've shown you are called static sea level. Gravity, there's no momentum here. Gravity just puts the water where it's supposed to go. And because of tidal mixing, that happens very quickly. It doesn't take a long time for those fingerprints to establish. But what people are looking at is a different question now, and that is, okay, we have your fingerprints, but you're also going to produce the dynamic changes. You're going to change ocean circulation, et cetera. What effect does that have on sea level? Because it will. And when does one dominate the other? And the answer is very complex. Close, there are regions on the Earth's surface, and the U.S. East Coast is one of them, in which these dynamic effects can play a dominant role in the change in sea level. They can dominate the sort of fingerprint that I showed you, right? None of it dominates if, and several papers have been written, and now this is the kind of rule of thumb, that if you have more than 10 centimeters of sea level rise, the static effects, the ones I've shown you, will dominate the dynamic effects, right? And that's important because if we're looking at 20th century sea level change, it means you have to worry about these dynamic effects, and nobody is worrying about them. And as I lamented to Bill last night, it was impossible to get modelers to run a few models that I think would shed a lot of light on 20th century sea level, because we know when these ice age models and these fingerprint models do poorly. And there are specific regions they just don't seem to fit. And the U.S. East Coast is one of them. And so it's a target for our group as a potential site where these dynamic effects are important. But we don't do those calculations. They're time-consuming. And you just have to get in the priority list for those runs. And we haven't done that. Right? We're Canadians. We don't yell. We're polite.
Other questions for our speaker? If not, thank you again.
Okay, that was
Thank you very much.
yeah.
We can turn this off and